And now we have a fun question. What's the size of the pumped storage facility? To put things into perspective, we've got a map here showing Steinmetz Falls, which is located in this upper corner. Here's the old hydro dam that we talked about, and the dam feeds into the Faraday River, which ultimately leads to the ocean. The pumped storage facility is located downriver next to the ocean right here. Right now I'm sketching in the upper reservoir. In fact, this is nothing more than a big hole in the ground, and when we were constructing it, it looked like a large open pit mine. The power plant itself is located down here, and the upper reservoir is connected to the power plant via pipes, which we call penstock. If we were to look at a sideways view, we would see the slope of the hill, the river, and the upper reservoir. The powerhouse is down here, and finally the penstock connects the upper reservoir down to the powerhouse. Now that we have a picture of what the facility looks like, we can calculate the capacity. So recall, we specified a 10 megawatt power rating, and we said it must provide that for 2 days. And for our purposes today, we're going to assume that this machine is 75% efficient. When we say something is less than 100% efficient, that just means that we don't get all of the energy back. For this pumped hydro system, we're going to put in electrical energy. The electrical energy is going to force the water uphill. Later, when we need it, that water will run downhill to give us electrical energy back. And all that efficiency means is that we're not going to get everything back that we put in. We're going to lose a quarter of our energy in the process. There's an equation that describes the output of our system. Power is equal to efficiency times the density of water times the flow rate times the gravitational acceleration times the height. And now we can assume some things about our system. We've specified that it's to provide 10 megawatts output power. The efficiency we said was 75%. Water has a density of 1,000. The flow rate, well, that's the thing we're looking for. Gravity is 9.81. And finally, let the height of our system be 30 meters. Solving for Q, 45 cubic meters of water every second. But that's not what we were looking for. We want to know the capacity, or the size of the reservoir itself. That calculation isn't too bad, because we know the rate at which the water is flowing out of it, and we also know the time, which is 2 days. And when we solve for this, we find that the capacity is 7.8 million meters cubed. I don't know about you, but I have a hard time visualizing how much water that is. So let's use the Olympic swimming pool and see how many pools are in that reservoir. Olympic swimming pool has these dimensions. It is 50 meters long, 25 meters across, and 2 meters deep, giving us 2,500 meters cubed. At that point, you can do a quick division, and you'll see that you need 3,120 pools to fill our reservoir. That number is still rather hard for me to comprehend, so let's try one more time. Let's try one more time with something that's a little easier to comprehend. Let's assume that this is 1 kilometer across and 4 meters deep. And now let's find out how long this would have to be in order to equal 3,120 pools. We would say that 7.8 million cubic meters is equal to 4 meters times 1 kilometer times some number n. And that number n is going to represent the length of this body of water. And when you work this out, n is equal to 1.9 kilometers. So there you have it. If we go back up to the reservoir, we can see that it's about 1 kilometer in this direction and about 2 kilometers in this direction and about 4 meters deep.